So now we are dealing with another aspect of this transition of marine robotics for from its pioneering phase to its mature phase. Before we discussed about the need of providing fair data, and now there is another aspect that is related to good experimental methodologies in marine robotics. Oh, it is not. Okay. So, before we focus on the data safety picture, now going back to the three pillars of sustainability, we consider the economic pillar, the industry, and the need for industry of good experimental methodologies. This is necessary also for science, because the concept of reproducibility and replicability as a continuum of practice is strongly pushed by the European Union in the last years. And the reproducibility and replicability of results as a value, both as a mechanism to ensure good science based on truthful claims and the driver of further discovery and innovation. An experiment is reproducible when you have the same data in same analysis. It is replicable when you have different data in same analysis. In our case, when you have a vehicle working at sea, it is impossible to perform two experiments with the same data. But we can have replicable experiments. And if you are interested to which are the guidance and so on in EU, you can find this document available on the network. So, we develop technology, but we are also researchers and we are scientists in robotics. And when you have the scientific process for scientific discovery ideal model, it has a conventional, traditional approach. You formulate an hypothesis, design the study, then run the study and collect data, analyze the data, and report your results. This is the scientific method. And you see, check in this way if your initial hypothesis is true or not, and if your study that you design is correct. What we usually did and do in marine robotics, we formulate an hypothesis, and this is okay. We design the study, yes. We design our algorithm, formula, necessità and so on, and usually we do it in the right way. But only in a few cases we design a set of replicable experiments. And in the past, these cases were more rare. Then implement and run the algorithms, of course. Analyze the data, of course. And, okay, write a paper. Usually, we write a paper with some graphs showing that the algorithm is working. This is what you usually find in the literature. So data will remain somewhere in our office, as I said before, hard disk, USB file, in a not well documented form, and low or poor quantity quantitative measurements of how much the algorithm works well is given. And this is typical of the literature. If you go to the literature of domain robotics, you find this. It is also comprehensible, because if you have to make a very strong effort to have the system working, to make some experiments and so on, and you have to face a lot of difficulties in performing experiments, and we will see them, it is almost normal to do that. This does not mean that you work in the wrong way. But now, since we can handle some problems in all this development process, we can focus more on these aspects. So, experiments are not carried out in the lab, but at field with a set of unpredictable constants. And this is quite important when we do this. We have environmental conditions, waves, wind, current. They can affect our experiments until the point of it is not possible to make the experiment today. Logistics, ship access, restricted water access, maybe in a traffic area. And also the time available to carry out the experiment. Ship access has high costs. Human resources devoted to carry out experiments have a significant cost. But for instance, just to say about environmental conditions, when performing experiments to characterize the hydrodynamics parameter of the catamaran we developed, we work in an area that is a kind of regatta field inside the Genova Harbor. It is a place where we can stay. We are in the Mediterranean, good weather and so on, but to perform this kind of test and identify hydrodynamics coefficient, we need to, with the surface people, we needed to have days with no currents, okay, Maria, the tide was not so high, and we could do that. No waves, it is a protected area. No wind. In that area, it's a nightmare. I had an almost perfect place where to carry out trials, but during all July months, I had 2 or 3 days available. But I am not God, I couldn't command the wind. So, when you are in these conditions, the temptation to take shortcuts is very strong. So, what we did was okay to develop a mature technology that has proven its usefulness and played the role of game changer in many fields of application. But now we need to move a step further. And to introduce good experimental methodology in marine robotics. This means that given the function we want to test, we have to define suitable performance indexes and the variables that we need to compute them. Then we need to design a set of replicable experiments to measure the defined performance, and also to define the variables required to understand environmental conditions. We have to measure and log them. And also to define operational procedures to perform in-field replicable experiments. And replicable experiments and the operational procedures are strictly we need to define experiments that we can execute at field. This is quite important in the design phase, because we are not in a MATLAB simulated environment where each time we can put the robot with its own dynamics and kinematics in a specific one. We have to reach the starting conditions of the experiment in a replicable way. And Sometimes it is not so easy. And we need to take into account these issues when we design the set of experiments. Otherwise, we cannot execute them in the right way. Okay, but does, again, the approach is, does it exist anything in other disciplines related to that? When we look at standards for ship maneuverability, the International Maritime Organization published standards for ship maneuverability with explanatory notes to the standards in December 2002. And these standards were developed for ships with traditional propulsion and steering systems, shaft-driven ships with conventional rudders. And they defined some standards maneuvers. Test speed of at least 90% of the ship's speed corresponding to 85% of the maximum engine output. Because all these standards and these maneuvers were defined with the goal of safety of maritime navigation. This is something similar to the crash test that they do on cars. The goal is not to identify the ship parameter. The goal is to establish the safety parameters of the ship. That is different. Turning circle, zigzag test, spiral maneuvers. And they define also the conditions at which the standards apply. Deep and restricted waters, so when we are in ocean, calm environment, full load, and steady approach at the test speed. So if you want to measure the turning circle of the vehicle once you have a fixed speed of the vessel and a fixed rudder angle, you start the test at the test speed, and then in steady state, and then you start to work. The criteria based on ship length and the speed and are the turning ability, initial turning ability, your checking and cruise keeping abilities, stopping ability. Basically, you need to know how to measure how the ship can maneuver to avoid an obstacle or to stop. There is a very specific nomenclature. In any case, all these standards are published and you can find them available on the network. And you have this specific maneuvers. Turning circle maneuver is to be performed both starboard and port. In standard with the rudder is 35 degrees rudder angle, or the maximum design rudder angle permissible at the test speed. Because you need to say, okay, I can make a turn that is small enough. But this means that I need this space to make a turn. Otherwise, I will crash. The rudder angle is executed following a steady approach with zero yaw rate, so you arrive moving forward and then straight forward, and then you start to turn. So basically, you have a tactical diameter. The diameter from when you start to the other, advance and transfer. When you have 90 degrees and the range along the moving direction of the beginning and the range from the straight line at the beginning and when you have to turn. Of course, if there is current, you don't execute a perfect turning circle, but you execute this kind of motion and you can estimate the current and compensate it to reduce it to a turning circle. Because basically, we are again, because you have the hydrodynamics of the ship is defined with respect to the water and not with respect to the ground, as we said also before. Then, zigzag maneuver. In this way, you see also the dynamics of your motion. And you can start it both starboard and port, and begins by applying a specific amount of rudder angle to an initially straight approach. The rudder angle is then shifted on one side and the other for a specific deviation from the original ship angle. In standards, there are two kinds of zigzag test, 10 degrees and 20 zigzag test. The first will use another angles of 10 degrees and the second of 20 degrees. Basically, what we do is to give 10 degrees, then when you have a shifting heading of 10 degrees, you move to -10 and so on. And you have basically oscillations. You can measure some variables here again as overshoot, initial turning time, and time to check you. There's some of the variables that you can measure and says how can you oscillate to this exactly. Then there are pull out and spiral maneuvers. This means that the pull out that at the end of your turning circle, you put everything to zero and you see how much the vehicle will move again straight forward. And direct spiral maneuver, you increase step by step the degree of the rudder, or you decrease step by step the degree of the rudder. And so, as I said before, we have different goals. Measuring these parameters from the point of view of ship architect and of having a safe maritime transportation is important to see it, because you say, okay, this ship has this maneuvering capabilities. And all the tests are defined on the basis of safety. But as marine roboticians, we are interested in something different, because we want to perform this test to characterize the dynamics of our ship, identify the dynamics parameters for designing effective and reliable guidance navigation control systems, and to characterize guidance and control algorithm performance indexes. This is different because we have also different tests. IMO test, they assume ship has normal features for the control of speed and heading, seven propeller and another. But however, most of the definitions and conclusions can be applied also to ships with other kinds of control activities. From the point of view of marine robotics, we have a small size vessel, often with other types of control operators, making the azimuth operators and so on. But we can, in any case, we can be inspired by this IMO test. And which is the idea? To develop modeling and identification procedures based on standards of ship maneuverability. So, for steady state hydrodynamics, if you use turning circle maneuvers, a different source force, and the other azimuth angle, plus pull out maneuvers, you can identify steady state parameters. Basically, the dynamics. For transient dynamics, zigzag maneuvers at different source force and other azimuth angle can help you in identifying the inertia of your ship. And we can combine for validating combined steady state and transient dynamics. We can use direct spiral maneuvers, different source force, and another azimuth angle, plus pull-out maneuvers, to use them to verify how good is the model that we identify. This is at the end a suggestion in order to perform tests that are in any case well coded from someone. And what I have to say is that also the preliminary test that we made was very similar to this. So, because the key point that we want for modeling identification procedures are the fact that the test has to be executed automatically. It would be great. Online validation of the quality of the maneuver, for instance, to check if steady state has been reached in order to optimize the time required to execute the test and the quality of results. What often happens, if you want, for instance, to say, okay, I put my robot in steady state, is that you stop and you are looking, you are seeing your robot moving. Usually you stop the test before reaching steady state in a stable way. We did it many times. So it is important to develop standard routines that monitor the robot executing identification and stop the robot when steady state is reached in a stable, very unstable conditions. And then to have an accurate description in log of experimental conditions. It would be good, for instance, we have not used it yet, but we are working on that, for instance, to have an anemometer to measure wind in the area where you are working, maybe also on board the vessel, considering that in that case it measures not only the wind but also the motion of the combined effect of wind and motion of the vehicle. So, for instance, we have an example is for experiment in straight line following to see which variables we can use as performance indexes. For instance, we have, if we follow a line in one direction and return back, we have a U-turn maneuver, and you have the L parallel and the L perpendicular that are the ranges, basically the rectangle inside which we perform the U-turn. Then, from there, we have a transient time to reach the target line when we start to move in this to approach it. And the overshoot, maximum overshoot during the transient. And then we have a settling time to reach it. To be again on the desired straight line and to reach steady state. For instance, an operational procedure that we used was to move forward and backward along a straight line. And why did we use that? And not to start from points at different ranges from that and so on. Because we work in this regatta field area, and we had a kind of row where we could work. So doing that, we were basically sure that the robot remained inside that row and we didn't go outside in an area where it couldn't enter. And in this way, we had basically the same initial condition for all the experiments. The only thing that changed was the direction of motion following the line. It was in one direction or the other. So in some way, the experiments were repeatable in an easy way. Of course, if you have space, you can repeat this experiment with the target straight line or with an orientation that covers all the directions in order to work with all the spread set of environmental disturbances. And we defined these performance indexes, compute them, and this is a first example of trying to do it in a well-defined way. So the variables of interest are the target line, 1 point on the line orientation, the estimated ESP position, adding yaw rate and linear speed, the reference yaw rate, in the case we have a dual loop guidance and control architecture, so line following provide the reference yaw rate and we have a control algorithm that control it, and the reference search force in your model. We have all this data, and with all this data we can compute experiments and execute replicable experiments. So as I said before, we perform the experiments, move back and forth along the segment for guaranteeing that the ASP remain inside the same area. We check when at that time when it reached the end, and then send the other toggle command for the line in the opposite direction and so on. And then we identify the end of the segment from the map of the test target. You can change the orientation of the target straight line, as I said before, and we can also have additional variables of interest as the reference and measure with orientation speed or azimuth rectangle and the top current to provide us also the computation, the possibility of computing performance indexes on how much power we consume or how much we stress the mechanics of the control system, probably to continue to ask the other to change orientation and so on. And also to check, to measure ASP pitch roll and to see if they affect in some way the performance of the line following algorithm. So this is an example, and this is a preliminary discussion on how we can perform trials and to move forward with experimental methodologies for many models. So I don't know if you have any questions on that.
Yeah. For the ESP model, you say that pitch and roll is only for disturbance rate. Yeah. For the model identification, can you do anything for this pitch and roll, or only measure for
the model and doing model with on board sensor-based identification and for the surface vehicle? Basically, we have not actuators for actuate pitch and roll on these vehicles. But of course, when you have if you have a wave, and usually when working in coastal areas, sometimes if you have strong waves, you cannot work. Basically, you also in lagoon, for instance, we work a lot in Venice lagoon and so on. You have waves when there are vessels moving around, probably at a high speed. And so, for instance, you can maneuver in performance could be affected. And also, especially, we are focusing on that if you have a multi-beam or a single beam ecosounder to measure range from the sea bottom. When you have a strong pitch and roll, the measurements are not reliable. So you need probably to move back to that place and collect measurements again. It would be better if you can detect it automatically instead than doing it 2 days later when you check your data in the lab. And so you say, okay, I have to go there again because I have a hole in my data set. So to identify possible holes in the data set in real time by the vehicle itself, it would be quite useful because at the end you will take maybe half an hour more to collect all the data set, but you don't need to go back there 1 week later, and so it is you consume a lot of time and resources, less time and resources. Okay?
I have 2 questions. One is a question. The first one, in terms of these experiments, and you say that you can publish papers with results, whatever, but do you use any other data forms to publish, let's say, things that are improvements, but are not like small improvements that you know that you.
I can answer with a question made many years ago by a reviewer. I published a paper on the control of the ROE, and a good question from the reviewer is, okay, but how can you say, what can you tell about the performance of your algorithm with respect to what they have with others? Okay, my answer was, okay, the only thing I found was that paper where they mentioned something, but there were some graphs, and you saw that performances were lower because you had more oscillations and so on, but they use a phantom robot with under-actuated actuation system, and that was very difficult to control because of how the actuators were mounted on that. So what I said I could write was, okay, it behaves better than that one, but probably in that one I don't know about the algorithm because the mechanical design of the robot and the actuation system is different, and we cannot compare them. And also, this is strictly related to the previous presentation, because if we can publish results of experiments from different robotics groups, and we can share them, we can move in this direction. At this time, the data are not available, but what I discovered is that also in the field of chip architecture, they have all this data, these things, they make testing in towing tanks and so on. The data they have are the graphs published in the papers, not the data sets. So we have to move to share data sets. Of course, okay, we are researchers, we are evaluated also on the basis of our papers, of the H-index of our papers, and of number of citations, impact factor, and so on. So we collect some data. It is reasonable to say, okay, we have this fair data with an embargo of 6-12 months because we need some time to publish first papers, and then okay. Then it will be, what will be cited will be the DOI of the data set. But we have to completely change our mentality for doing that. And in any case, my opinion is that is the time when to do that.
Yeah, I think one of the problems we have in mind science is also that when you spend time in getting your data open or shareable, you don't get paid for that. You get paid for the paper, not for losing time, no, but spending time in sharing your data. And that, because one of my questions was related with, let's say, for example, the arm that you designed to collect the ribosome.
Yeah.
So you develop all that stuff and you test. Probably you use one and doesn't work and whatever. All that information, perhaps in the robotic area, I don't know, because in marine biology we have some websites where you can share protocols that are not peer reviewed, but you can share how you obtain the results in terms of.
We have not it yet,
Okay.
and but we need to push to have it. I think we had this. We exchange opinions, we exchange a lot of experience between people, but basically we are not so structured to have them in a publishable way. We need to make an effort on this direction. Now we can do that because the robot is working, so we can focus on that. Before we had to focus on having the robot working, and so it is. That's the reason because I think that that's the time of doing that. So.
And my second question was related to this that you talk about sharing with people. In your long experience with designing robots for underwater or for the sea, do you have examples where you talk with, I don't know, fishermen or captains of the boats or whatever, people that have a lot of empirical work in the sea, and they give you like a tip or whatever, and you improve your design? Do you have any example of that?
That suggested us good things.
Yeah, like we were talking with a fisherman that, I don't know, in this role you can add this. And
Basically, we have always hints from somebody. I have not an example, probably because it is not only one. But for instance, for designing the vehicle for very shallow water, we had discussing with people of the hydrographic and institute and other people doing maps, mathematic maps in lagoons and so on. We discovered that the problem are the first 3 meters, where it is when you have a 1 meter and so on, where you do the job having one guy going inside the water with a pole, and we should avoid that. And this was, for instance, a reason to push to have something in the other direction. So there are other things that you talk with anybody working at sea, because, for instance, you saw we don't like to have things and this kind of things. And if you look at our robots, we have all the propellers, all the actuators inside the frame of the robot. Because when you deploy it with a crane, with a boat, it is quite easy to have very sudden waves of wind and you can crash against the wall of the boat and destroy everything. And you, especially if you are in harsh environments, you need to have a safe robot from that point of view. Also to keep all the motors inside the hull when you are in shallow water, for instance, from that, and so on. So, and in many cases, for instance, for the winches, when I mentioned that we are very lucky because we have very good technicians with a lot of experience in these conditions, we bought these winches for a fisherman. And a small brushless motor, designed the mechanics to adapt it, and we had the winches for the balloon and the underwater multiparametric gauge. They are very small, didn't cost a lot, very effective. So these are basically the things, and also there are exchanges of experiences between roboticians saying this is working, this is not working. If you follow this approach, theoretically it works, but we had a lot of problems doing that and this kind of things.
Tenemos una pregunta desde el chat. Does it exist an online simulation system or tool to maneuvering a ROS or IUV?
I don't know. We have not yet, but we are completing a tool for simulation of our surface vehicle now. But and the plan is in a few months to make it available. And and each one can install it on a Linux machine, compile it and run it in its own lab. To have them working online, they need. I know that there were some experiences in the past, but in this case, you maneuver completely the vehicle from remote. So you have this time variant delay between your control system connected to the vehicle and the simulated vehicle, because there is an internet connection between them. So for instance, from our point of view, if we want to develop a navigation guidance and control system, we want to have the simulator connected in a narrow in the loop way to the control system. So there are this kind of differences. But for instance, there are also, maybe we can see them. If this is concluded, we can move to 5 trees, simple trees presentation. Where, because if we have just a bit of time, we can see some other applications of marine robotics. Have you any other questions on good experimental methodologies? Now we have some other applications for instance, robotics for the safety of maritime transportation. And were involved in two projects funded by EC, Minoras and CAR. On the left, you see Minoras, where we developed a magnetic roller to measure, to monitor the state of the tanks on ships, and basically to measure with ultrasonic, to provide visual inspection and to measure the thickness of the plates due to corrosion. And the table you see is basically for safety, but the robot would climb the iron wall using this magnetic roller. And on the right, we use the cooperative robotics to recover emergency towing devices released by distressed ships. And it was a project again where we could do that. And basically we had, when you have a distressed ship, they release an emergency towing device that in many cases will remain close to the hull of the distressed ship. And people move from the tugboat with a dinghy to go there to collect this emergency towing device, carry it on board the tugboat, then they recover the messenger rope and then the force rope and so on. The idea is to have this device put in water and to go with the semi-submersible vehicle with the tether, maneuver around this emergency towing device with the vehicle, making a knot with the tether, and then recover the autonomous surface vehicle and the emergency towing device, as in this way you see. So this was the idea, and so you can do the maneuver without sending people at sea. Other kind of applications are related to riverine robotics, because we always talk about marine robotics, but basically it is waterborne robotics. We can use these robots not only at sea, we can use these robots also for rivers and lakes. And there are a lot of applications in rivers and lakes, and also probably the possibility of using more electromagnetic propagation, because in fresh water it is better than in salt water. In this case, you see the portable vehicle. My colleagues were able to reach the river in this mountain area in Liguria, and it was possible to collect data to have a bathymetric map of the river when the water is very shallow, close to the sea, and also in the mountain part where it was so difficult to assess this area. And we have also other applications that are called the remote visit of sites of interest from non-mobile. And we had this European project that was Blue Roses, and the idea is to be able to control the robot from your mobile in sites that could be of interest, because they are archaeological sites or harbors and so on. So on the left, we see a semi-submersible vehicle piloted from the vehicle was in Viareggio Harbor in Italy, and the guys with the mobile phone were in Algarve, south of Portugal. And it was possible to do that. On the right, you see images when we do the experiment on the other direction, in this case with a blue ROV of the Instituto Superior Técnico de Lisbon, and in the south of Portugal, in Algarve, they sank some old boats of the Portuguese Navy, and used these sank ships to have a kind of diving center, because leaving them for a few years, they were populated by underwater fauna and flora, and it is a very nice site close to the coast for divers. And in this case, there is the exploration made with computer, but it is also possible with meet in Dubai, from my colleague in Viareggio, he explored the underwater site, this sailed ship in south of Portugal. So this was a way of showing that it is possible to have also, how to say, a kind of use of robotics for entertainment, for remote visit, to see if it is possible to use it also for goals that are just a bit different from the usual ones that we have. And there was also some interest on that, trying to understand how to use it also during pandemic. Then two operators moved back to standard things until next pandemic, when they will say, okay, we have no money. Okay, but you didn't do anything for doing something when there is a pandemic. But okay, this is the mentality of the tech sector, that in any case is 70% of blue economy, at least in Italy, so it is a lot. Because 70% of blue economy is made by hotels and restaurants. So these were some other things, and thank you very much.
No, there is a comment
okay.
from Lucy commented to the previous question. He said, okay, thanks for the answer. That may be important for us to practice how to set everything up and use it properly in special environmental conditions before getting in the ship.
Yes, and it is quite important to have the so-called algorithm simulation, because if you identify your system, what I usually do is to have worse conditions in simulation than at sea. For instance, I increase the noise of the sensors, I increase the probability of having outliers, and so on. So in this way, you can, with algorithm the loop simulation, you can check if you made some simple mistakes in your implementation. For instance, a wrong sign, things that always happen when you make, when you write code. And also to tune the parameters of your algorithm in a way that the system can work when it is at sea. Also, if you have mission control, you have to do all of that. And if you have time enough, what I suggest, even if it could be just a bit boring, is to perform your mission before inside your algorithm the loop simulation environment, and then go to it to see. You recover a lot of time at the end. And also to have open algorithm the loop simulation environment would be also a good way to have cooperation with a research group who have the vehicles, because you can run on your machines the algorithm the loop simulation, the navigation and control system that is of the vehicle. You can add the algorithm that you want to develop and test, so you can test and check your ideas. For instance, of course, with the support of the people that owns the vehicle. And then, when everything is working in simulation, that is a realistic, real-time simulation, then people can perform tests at sea. And this is, for instance, a way, I think we can discuss it better next Thursday during the workshop, but this is a way that we experimented also with Charlie in the previous years, and it is a very good way for cooperating with a research group that don't have prototypes. But this could allow to do a lot of work, very good work, and so on. So for instance, when in 2009, there was an IPAC conference in robotics in Brazil, we had a whole session about the cooperation we had with other research groups using Charlie USB as a prototype for testing algorithms. And at the end, also having other things, So basically, we had 9 papers in cooperation with other groups in that conference. This is quite good for research group as ours, because, for instance, in our case, we are not a university, so we have no students. And it is also good for people beginning to do things, because you can cooperate, you can start to do things, sharing resources and accessing resources with the research groups who already have their facilities. So,
Ok, so, por hoy hemos terminado. Muchas gracias. Bueno, nos vemos mañana. Mañana va a ser la primera parte del día como muy técnica. Ah, ¿hay una pregunta? No, de la diapositiva. ¿De la? Diapositiva. Ah, sí, sí. Bueno, las diapositivas están subidas a la página. Digamos, van a tener el material en la página de Robótica y después en el canal YouTube se van a subir las clases grabadas. No, quería decir que mañana va a ser un día bastante, la primera parte, bastante técnico, con muchas fórmulas, ¿no? Mañana.
tomorrow it will be identification, guidance, control, and motion simulation.
Y después a las 12 menos cuarto, hablarán el personal de Marisco, que es una empresa que va a traer un ROV y que se verá el jueves en Pileta, y van a hablar de las aplicaciones de la robótica en la industria, en la defensa, en ciencia, y va a ser muy interesante. Así que mañana va a ser un día bastante intenso, pero esperemos que provechoso. Así que muchas gracias y nos vemos mañana.